Have you ever wondered why car radiators have these thin metal plates or why your laptop has those aluminum ridges? Today, we're diving into one of the most practical concepts in heat transfer, extended surfaces, also known as fins. By the end of this video, you'll understand exactly why engineers add fins to surfaces, how to analyze them mathematically, and how to determine if a fin design is actually effective. And stick around until the end. I've prepared 8 complete problem solutions that will test your understanding of everything we cover today. Let's get started. First, let's understand the problem. Imagine you have a hot surface that needs to cool down by transferring heat to the surrounding air. The heat transfer rate depends on 3 things: the convection coefficient, H, the surface area, A, and the temperature difference. Now, if your convection coefficient is low, like with air cooling, and you can't increase the temperature difference, what's your only option? Increase the surface area, but you can't make your base surface bigger. So what do? You extend the surface by adding fins. Fins are simply extended surfaces that increase the heat transfer area without increasing the base surface dimensions. They're incredibly effective when the convection coefficient is low. Let's see where we use them in real life. Economizers in steam power plants, maximizing heat recovery. Car radiators, those thin plate fins you saw earlier. Air-cooled engine cylinder heads, motorcycles and lawnmowers. Electric motor bodies, preventing overheating during operation. Compressors, maintaining optimal operating temperature. Refrigerator coils, both cooling and condenser coils. Wherever you see poor natural convection but need efficient cooling, you'll likely find fins. Now let's look at the different types. Fins come in various shapes depending on the application. Let's look at the 4 main types. First, straight fins. These extend straight out from the surface. They can have uniform cross-section, like a rectangular plate with constant thickness, or non-uniform cross-section, tapered or triangular, getting thinner toward the tip. Second, annular fins. These are circular fins that wrap around tubes or pipes. You'll see these in heat exchangers and on engine cylinders. Third, pin fins. These are cylindrical rods extending from the surface. They're compact and often used in arrays for electronic cooling, like in CPU heatsinks. Fourth, innovative designs. Modern engineering has created optimized fin patterns that maximize surface area while minimizing material and weight. For our analysis today, we'll focus on straight fins with uniform cross-section. They're the most common and easiest to understand mathematically. Now comes the interesting part, the mathematics. But don't worry, we'll build this step by step. And remember, I have 8 detailed problems waiting for you after this theory section. Before we analyze, we need to make some assumptions to simplify the problem. Key assumptions: steady state, meaning temperature doesn't change with time. No internal heat generation, the fin itself doesn't produce heat. Uniform convection coefficient, H, same all over the surface. Constant thermal conductivity, K, material properties don't change. One-dimensional conduction, heat flows only along the length. Negligible radiation, we only consider convection. Now, let's look at a small element of the fin. Heat enters from one side, heat leaves from the other side, and heat is lost to the surrounding fluid from the surface. When we write the energy balance and apply Fourier's law and Newton's law of cooling, we get a differential equation: d squared theta over dx squared minus m squared theta equals 0, where theta is the excess temperature. That's the difference between the fin temperature and the fluid temperature. Theta equals T minus T infinity. This m squared parameter is crucial. It's defined as m squared equals h times p over k times AC, where h is the convection coefficient, p is the perimeter of the fin, k is the thermal conductivity, and AC is the cross-sectional area. Think about what m represents. A large M means high convection or low conductivity, temperature drops quickly along the fin. A small m means low convection or high conductivity, temperature stays more uniform. The general solution to this differential equation is theta of x equals c1 times e to the mx plus c2 times e to the minus mx. But here's the key. We need boundary conditions to find c1 and c2. And different physical situations give us different boundary conditions. That leads us to 4 important cases. Depending on what's happening at the fin tip, we have 4 different scenarios. Let's go through each one. Case 1, very long fin. If the fin is extremely long, the temperature at the far end approaches the fluid temperature. Mathematically, theta approaches 0 as x approaches infinity. Theta equals theta b times e to the minus mx, where theta b is the temperature at the base. The heat transfer rate is Q equals root h times p times k times ac times theta b. Case 2, insulated tip. This is the most common case in practice. The fin tip is insulated, meaning no heat flows out from the end. Mathematically, d theta over dx equals 0 at x equals L. Theta equals theta b times cosine m times L minus x over cosine ml. The heat transfer is Q equals root h times p times k times ac times theta b times tangent ml. Notice that extra tangent ml term there. That's accounting for the finite length of the fin. Case 3, fixed temperature at tip. Sometimes the fin tip is held at a constant temperature. Maybe it's attached to another surface. This case is less common but mathematically possible. Case 4, convection at tip. This is the most realistic case. The fin tip also loses heat to the fluid. The boundary condition is minus k times d theta over dx equals h times theta at the tip. Here's a practical trick. We can simplify case 4 by using a corrected length. For rectangular fins, length corrected equals length plus t over 2. For cylindrical fins, LC equals L plus d over 4, where t is the thickness, d is the diameter. Now we can treat it like case 2 with this corrected length, much easier for calculations. Now, here's a critical question. How well does the fin actually perform? That's where fin efficiency comes in. Imagine if the entire fin could be maintained at the base temperature. That would give us maximum possible heat transfer. Qmax equals h times AFIN times theta b. But in reality, the temperature drops as we move along the fin, so we transfer less heat. Fin efficiency is the ratio eta fin equals Q actual over Q max. More specifically, eta fin equals tangent ml over ml. Look at this graph. As ml increases, efficiency decreases. Why? Because large ml means the fin is either very long or has high convection, but low conductivity. This causes a steep temperature drop. The tip region contributes very little to heat transfer. In practice, we want fin efficiency above 0.6 or 60% for the fin to be worthwhile. This tells us don't make fins too long. There's a diminishing return. Efficiency tells us how well the fin performs relative to its ideal, but effectiveness answers a different question. Is it even worth adding the fin in the first place? Fin effectiveness is defined as epsilon equals Q with fin over Q without fin. More specifically, epsilon equals Q fin over H times AC times theta b. The denominator is what you'd get from just the base area without the fin. Here's the rule of thumb. Epsilon less than 2, not worth it. You're barely doubling the heat transfer. Epsilon equals 2 to 3, marginal benefit. Epsilon greater than 3, good, the fin is definitely helping. Epsilon greater than 10, excellent performance. For a long fin, effectiveness simplifies to epsilon equals radical k times p over h times ac. Look at this carefully. Fins are most effective when k is large, use materials like aluminum or copper. H is small, fins work great for air cooling, not so much for liquid cooling. P over AC is large, thin fins with lots of perimeter. This is why you'll never see fins on the inside of a boiler where water is boiling. The convection coefficient is already huge. But for air cooling, fins are essential. All right, let's wrap up what we've learned today about extended surfaces. Key takeaways. First, fins increase heat transfer by extending surface area where convection is limiting. Second, 4 main types: straight, annular, pin fins, and innovative designs. Choose based on your application. Third, 4 analytical cases based on tip condition. Very long fin, insulated tip, most common, fixed temperature, convection tip, use corrected length. 4, fin efficiency tells you how well the fin performs relative to ideal, aim for eta greater than 0.6. 5, fin effectiveness tells you if the fin is worth adding, need epsilon greater than 2 to 3. 6, design wisdom, use high conductivity materials, keep fins reasonably short, and remember, fins work best when convection coefficient is low. Alright, now here's where the real learning happens. Theory is great, but you truly understand a concept when you can solve problems with it. I've prepared 8 comprehensive problems covering everything we just discussed. Different fin geometries, all 4 boundary condition cases, efficiency and effectiveness calculations, real-world design scenarios, and material selection problems. Each problem is solved step by step with clear explanations. By the end, you'll be a fin analysis expert. Before we jump in, if you found this theory helpful, please hit that like button. It really helps the channel grow. And if you're serious about mastering engineering concepts, subscribe to Academic Engineering and ring that bell so you never miss our detailed problem-solving sessions. Also, drop a comment below telling me which type of fin problem you find most challenging. I read every comment and use your feedback to create better content. All right, engineers, grab a pen and paper. Let's solve some problems and solidify your understanding of heat transfer through fins. Let's begin with problem 1. Consider a very long rectangular fin attached to a flat surface such that the temperature at the end of the fin is essentially that of the surrounding air, which is 20 degrees Celsius. The fin has a width of 5.0 centimeters, a thickness of 1.0 millimeters, and a thermal conductivity of 200 watts per meter Kelvin. The base temperature is 40 degrees Celsius, and the heat transfer coefficient is 20 watts per meter squared Kelvin. We need to find 3 things. First, the parameter m. Second, the temperature at a distance x equals 5 centimeters from the base. And third, the rate of heat loss from the entire fin. Now, let's organize our given data. Here's what we know. The surrounding temperature, T infinity, is 20 degrees Celsius. The width of the fin is 5 centimeters, or 0.05 meters. The thickness of the fin is 1 millimeter, or 0.001 meters. The thermal conductivity of the fin is 200 watts per meter Kelvin. The base temperature is 40 degrees Celsius, and the heat transfer coefficient, H, is 20 watts per meter squared Kelvin. And we're examining a distance of 5 centimeters, or 0.05 meters from the base. Let's solve this problem step by step. Step 1. Calculate the perimeter of the fin. The perimeter of a rectangular fin is given by 2 times the sum of width plus thickness. Substituting our values, 2 times, open bracket, 0.05 plus 0.001, close bracket. This equals 0.102 meters. We'll add this calculated value to our data. The perimeter of the fin is 0.102 meters. Step 2. Calculate the cross-sectional area. The cross-sectional area equals width times thickness. That's 0.05 times 0.001, which gives us 5 times 10 to the power of negative 5 square meters. Adding this to our data, the cross-sectional area of the fin is 5 times 10 to the negative 5 square meters. Step 3. Calculate the parameter m. This is our first answer. The parameter m is calculated using the formula m equals the square root of h times p fin divided by k fin times a fin. Substituting our values, the square root of 20 times 0.102 divided by 200 times 5 times 10 to the negative 5. This gives us m equals 14.3 per meter. And there's our first answer. Parameter m equals 14.3 per meter. Step 4. Find the temperature at x equals 5 centimeters from the base. For a long fin, we use the exponential temperature distribution formula,
t minus t infinity divided by t base minus t infinity equals e to the power of negative m times x. Substituting, t minus 20 divided by 40 minus 20 equals e to the power of negative 14.3 times 0.05. Solving for t, we get 29.79 degrees Celsius. Perfect. Our second answer. The temperature at 5 centimeters from the base is 29.79 degrees Celsius. Step 5. Calculate the rate of heat loss. For a very long fin, the heat transfer rate is Q dot equals the square root of H times P fin times K fin times A fin times the temperature difference, T base minus T infinity. Plugging in our numbers, the square root of 20 times 0.102 times 200 times 5 times 10 to the negative 5 times 20, this gives us Q dot for a long fin equals 2.856 watts. Excellent. Our third and final answer. The rate of heat loss from the long fin is 2.856 watts. Let's summarize our final answers. Number 1, the parameter m equals 14.3 per meter. Number 2, the temperature at 5 centimeters from the base is 29.79 degrees Celsius. And number 3, the rate of heat loss from the long fin is 2.856 watts. And that completes our analysis of heat transfer through extended surfaces.
Let's examine problem 2. Aluminum fins with thermal conductivity of 200 watts per meter Kelvin having rectangular profile are attached on a plane wall with 5 millimeter spacing. This means there are 200 fins per 1 meter width. The fins are 1 millimeter thick and 10 millimeters long. The wall is maintained at a temperature of 200 degrees Celsius, and the fins dissipate heat by convection into the ambient air at 40 degrees Celsius, with a heat transfer coefficient of 50 watts per meter squared Kelvin. We need to determine two things. Part A, the fin efficiency, and Part B, the total heat loss from 200 fins per square meter of the wall. Important note, we will neglect the heat loss from the tip of the fin. First, let's compile our given data. Here's all the information we have. The surrounding temperature, T infinity, is 40 degrees Celsius. The length of the fin is 10 millimeters or 0.01 meters. The width of the fin is 1 meter, which we assume for our calculations. The thickness of the fin is 1 millimeter or 0.001 meters. The thermal conductivity is 200 watts per meter Kelvin. The base temperature is 200 degrees Celsius. The heat transfer coefficient, H, is 50 watts per meter squared Kelvin. And the number of fins is 200. Let's work through this problem systematically. Step 1. Calculate the perimeter of the fin. The perimeter of our rectangular fin is 2 times the sum of width plus thickness. Substituting our values, 2 times, open bracket, 1 plus 0.001, close bracket. This gives us 2.002 meters. We'll record this calculated value. The perimeter of the fin is 2.002 meters. Step 2. Calculate the cross-sectional area. The cross-sectional area is simply width times thickness. That's 1 times 0.001, which equals 1 times 10 to the negative 3 square meters. Adding this to our data, the cross-sectional area is 1 times 10 to the negative 3 square meters. Step 3. Calculate the parameter m. Parameter m is given by the square root of h times p fin divided by k fin times a fin. Substituting our known values, the square root of 50 times 2.002 divided by 200 times 1 times 10 to the negative 3, this yields m equals 22.372 per meter. We'll use this parameter to calculate our fin efficiency. Step 4. Calculate the efficiency of the fin. This answers part A of our problem. For a fin with adiabatic tip, the efficiency is eta equals hyperbolic tangent of m times L divided by m times L. Plugging in our values, hyperbolic tangent of 22.372 times 0.01 divided by 22.372 times 0.01. This gives us an efficiency of 0.984 or 98.4%.
Excellent. That's our answer to part A. The fin efficiency is 98.4%, which indicates this is a highly efficient fin design. Step 5. Calculate the heat loss from each individual fin. The heat transfer from a long fin with adiabatic tip is Q equals the square root of H times P times K times A multiplied by the temperature difference T base minus T infinity multiplied by hyperbolic tangent of M times L. Substituting, the square root of 50 times 2.002 times 200 times 10 to the negative 3 times 160 times hyperbolic tangent of 0.22372, this gives us Q for adiabatic tip equals 157.54 watts per fin. Now we can calculate the total heat loss from all 200 fins. Step 6. Calculate the total heat loss from 200 fins. This answers part B. The total heat transfer rate is simply Q dot total equals the number of fins times the heat loss per fin. That's 200 times 157.54. This equals 31,508 watts, or 31.51 kilowatts. Perfect. That's our answer to part B. The total heat loss from 200 fins is 31.51 kilowatts. Let's review our final answers to this problem. Part A, the fin efficiency is 98.4%. Part B, the total heat loss from the array of 200 fins is 31.51 kilowatts. This demonstrates the effectiveness of extended surfaces in enhancing heat transfer. The high efficiency of 98.4% shows that these fins are performing excellently, transferring a significant amount of heat from the wall to the surrounding air. Thank you for following along.
Let's look at problem 3. The following data refers to aluminum square fins that are provided on the surface of a semiconductor electronic device to carry 1 watt of energy generated by the device. Our objectives are to determine, first, the number of fins required to carry out this duty, and second, the fin efficiency. Please note we will neglect the heat loss from the tip of the fin in our calculations. Let's review the given data for this problem. The surface temperature is 80 degrees Celsius. The surrounding temperature is 40 degrees Celsius. The cross-sectional area of the fin is 0.5 millimeters by 0.5 millimeters, which equals 2.5 times 10 to the power of minus 7 square meters. The length of the fin is 10 millimeters, or 0.01 meters. The thermal conductivity of aluminum is 200 watts per meter Kelvin, and the heat transfer coefficient is 15 watts per square meter Kelvin. Now let's begin with step 1. Calculate the perimeter. For a square fin, the perimeter equals 4 times the side length, which is 4 times 0.5 millimeters. This gives us a perimeter of 2 times 10 to the minus 3 meters. More precisely, the perimeter is 2.002 times 10 to the minus 3 meters. We'll add this calculated value to our given data for future reference. Moving to step 2, we need to calculate the M parameter, which is a characteristic dimension for fin analysis. The formula for M is the square root of H times P divided by K times A. Substituting our values, M equals the square root of 15 times 2.002 times 10 to the minus 3 times the quantity 0.5 plus 0.5, all divided by 200 times 2.5 times 10 to the minus 7. After calculating, we get M equals 24.5 per meter. Again, we'll store this important parameter in our data box. Step 3. Calculate the number of fins required to dissipate 1 watt. For an adiabatic tip condition, the heat transfer equation is Q equals N times the square root of H times P times K times A multiplied by the temperature difference T base minus T infinity times hyperbolic tangent of M times L. Since we need to dissipate 1 watt, we substitute 1 equals N times the square root of 15 times 2.002 times 10 to the minus 3 times 200 times 2.5 times 10 to the minus 7, multiplied by the temperature difference of 80 minus 40 times tan of 24.5 times 0.01.
This simplifies to 1 equals n times 0.01174. Solving for n equals 1 divided by 0.01174, which gives us 84.93. Rounding up to the nearest whole number, we need 85 fins. Finally, step 4, calculate the fin efficiency. For an adiabatic tip, fin efficiency, eta equals hyperbolic tangent of m times L divided by m times L. Substituting our values, eta equals tan of 24.5 times 0.01 divided by 24.5 times 0.01. This gives us an efficiency of 0.98046 or 98.05%. This is an excellent efficiency, indicating that our fins are performing very effectively. Let's summarize our final answers. The number of fins required to dissipate 1 watt of heat is 85 fins, and the fin efficiency is 98.05%. This concludes our analysis of heat transfer through extended surfaces.
Problem 4. A motor body is 360 millimeters in diameter on the outside and 240 millimeters long. Its surface temperature should not exceed 55 degrees Celsius when dissipating 340 watts. Longitudinal fins of 15 millimeter thickness and 40 millimeter length are proposed. The convection coefficient is 40 watts per square meter degree Celsius. Atmospheric temperature is 30 degrees Celsius. Thermal conductivity of fin material is 40 watts per meter degree Celsius. Determine the number of fins required. Here we see a cylindrical motor body with an attached longitudinal fin. The motor surface is at 55 degrees Celsius. The fin has a thickness of 15 millimeters and extends 40 millimeters outward from the motor surface. Heat is conducted through the fin and then convected to the surrounding air at 30 degrees Celsius. Let's organize our given data. Motor diameter, 360 millimeters, which equals 0.36 meters. Motor length, also the fin width, 240 millimeters or 0.24 meters. Base temperature, 55 degrees Celsius. Total heat dissipated, 340 watts. Fin thickness, 15 millimeters or 0.015 meters. Fin length, 40 millimeters or 0.04 meters. Heat transfer coefficient, 40 watts per square meter Kelvin. Ambient temperature, 30 degrees Celsius. Thermal conductivity of fin material is 40 watts per meter degree Celsius. We'll store our calculated values in this box on the right as we solve the problem step by step. Now let's begin the solution. Step 1. Calculate the cross-sectional area of the fin. The cross-sectional area, A sub fin, equals B sub fin times T sub fin. Substituting our values, 0.24 meters times 0.15 meters, this gives us 3.6 times 10 to the power of -3 square meters. This value now appears in our calculated value section. Step 2. Calculate the perimeter of the fin. The perimeter P sub fin equals 2 times the quantity B sub fin plus T sub fin. Substituting, 2 times the quantity 0.24 plus 0.15. This equals 2 times 0.255, which gives us 0.51 meters. The perimeter is added to our calculated values. Step 3. Calculate the fin parameter m. This is an important dimensionless parameter in fin analysis. M equals the square root of h times p sub fin divided by k sub fin times a sub fin. Substituting our values, the square root of 40 times 0.51 times 40 times 10 to the -3 divided by 3.6. Evaluating the numerator, 40 times 0.51 equals 20.4. The denominator, 40 times 3.6 times 10 to the -3 equals 0.144. Taking the square root of 20.4 divided by 0.144 gives us m equals 11.9 per meter. Parameter m is now stored. Step 4.
Calculate two dimensionless parameters needed for the fin efficiency formula. First, ml, 11.9 per meter times 0.04 meters equals 0.476. Second, h divided by m times k sub fin, 40 divided by the quantity 11.9 times 40, which equals 40 divided by 476, giving us 0.084. Both dimensionless parameters are now stored. Step 5. Calculate the heat loss from a single fin. We use the fin heat transfer equation. Q dot fin equals the square root of h times p times k times a sub c multiplied by t base minus t infinity multiplied by a hyperbolic correction factor. The correction factor is sinh of ml plus h over mk times cosh of ml, all divided by cosh of ml plus h over mk times sinh of ml. Substituting our values, the square root term, square root of 40 times 0.51 times 40 times 3.6 times 10 to the negative 3, this simplifies to the square root of 293.76, which equals 17.14. The temperature difference, 55 minus 30 equals 25 Kelvin. Now the hyperbolic correction factor. The numerator, sinh of 0.476 plus 0.084 times cosh of 0.476. Sinh of 0.476 is 0.4939. Cosh of 0.476 is 1.1152. So we have 0.4939 plus 0.0937, which equals 0.5876. The denominator, cosh of 0.476 plus 0.084 times sinh of 0.476, which is 1.1152 plus 0.0415 equals 1.1567. The correction factor equals 0.5876 divided by 1.1567, which is 0.508. Therefore, Q dot fin equals 17.14 times 25 times 0.508, which equals 21.77 watts. Each fin dissipates 21.77 watts. Step 6. Determine the number of fins required. The number of fins, n, equals Q dot total divided by Q dot fin. Substituting 340 watts divided by 21.77 watts per fin. This gives us 15.61 fins. Since we cannot install a fractional fin, we round up to 16 fins. Therefore, 16 fins are required. This is our final answer.
Let's look at problem 6. A 5 mm thick and 45 mm long fin has its base on a plain slab maintained at 125 degrees Celsius. The surrounding ambient temperature is 25 degrees Celsius. The thermal conductivity of the fin material is 55 watts per meter Kelvin, and the convection coefficient of heat transfer between the fin and surrounding is estimated to be 145 watts per meter squared Kelvin. We assume the fin width to be unity, and there is convective heat loss at the end of the fin. We need to determine three things. First, the temperature at the end of the fin. Second, the temperature at the middle of the fin. And third, the rate of heat dissipation from the fin. Let's organize our given data. The length of the fin, L, is 45 millimeters, which equals 0.045 meters. The width of the fin, B, is 1 meter since we're assuming unity width. The thickness of the fin, T, is 5 millimeters, which equals 0.005 meters. The surface or base temperature, T subscript B, is 125 degrees Celsius. The surrounding ambient temperature, T subscript infinity, is 25 degrees Celsius. The thermal conductivity of the fin material is 55 watts per meter Kelvin, and the convection coefficient of heat transfer between the fin and surrounding is estimated to be 145 watts per meter squared Kelvin. We assume the fin width to be unity, and there is convective heat loss at the end of the fin. Calculate the cross-sectional area of the fin. The cross-sectional area, A, equals the width times the thickness. Substituting our values, A equals 1 times 0.005. This gives us 0.005 square meters. We'll add this calculated value to our data box for future reference. Step 2. Calculate the perimeter of the fin. The perimeter, P, equals 2 times the sum of width plus thickness. Substituting, P equals 2 times open parentheses 1 plus 0.005 close parentheses. This gives us 2.01 meters. Again, we'll save this value in our data. Step 3. Calculate the parameter m. The parameter m equals the square root of h times p divided by k times a. Substituting our values, m equals the square root of 145 times 2.01 divided by 55 times 0.005. After calculating, we get m equals 32.47 per meter. This is an important parameter that characterizes the fin's performance. Let's add it to our data. Step 4. Calculate the value of m times L. M times L simply equals m times L. That's 32.47 times 0.045. This gives us m times L equals 1.461. This dimensionless parameter will be used in our temperature calculations. Step 5. Calculate the ratio h over m times k. H divided by m times k equals 145 divided by 32.47 times 55. This gives us 0.0812. This is another dimensionless parameter needed for our short fin equations. Let's save this value as well. Now we're ready for answer 1, the temperature at the end of the fin, where x equals L. For a short fin with convective boundary conditions, the temperature distribution is given by T subscript L minus T subscript infinity divided by T subscript B minus T subscript infinity equals cosh of m times open parentheses L minus x, close parentheses, plus h over m times k times sine of m times L minus x, close parentheses, all divided by cosh of m times L plus h over m times k times sine of m times L. At the end of the fin, where x equals L, the numerator simplifies. Substituting our values, T subscript L minus 25 divided by 125 minus 25 equals 1 plus 0.0812 times 0, all divided by cosh of 1.461 plus 0.0812 times sine of 1.461. Solving this equation, we get T subscript L equals 66.04 degrees Celsius. This is our first answer. Now for answer 2, the temperature at the middle of the fin, where x equals L over 2. we use the same temperature distribution equation. Now, T subscript 2 minus T subscript infinity divided by T subscript B minus T subscript infinity equals cosh of m times open parentheses L minus L over 2, close parentheses, plus H over m times K times sine of m times L over 2, close parentheses, all divided by cosh of m times L plus H over m times K times sine of m times L. Substituting our values, T subscript 2 minus 25 divided by 125 minus 25 equals cosh of 0.7305 plus 0.0812 times sine of 0.7305, all divided by cosh of 1.461 plus 0.0812 times sine of 1.461. Solving this, we get T subscript 2 equals 80.14 degrees Celsius. Notice that the middle temperature is higher than the end temperature, which makes physical sense, as we move closer to the hot base. Finally, answer 3. The rate of heat dissipation from the fin. For a short fin with convective heat loss at the end, the heat transfer rate is given by Q equals the square root of H times P times K times A times T subscript B minus T subscript infinity multiplied by the correction factor, which is tan of m times L plus H over m times K, all divided by 1 plus H times m times K times tan of m times L. Substituting all our values, Q equals the square root of 145 times 2.01 times 55 times 0.005 times 100 times tan of 1.461 plus 0.0812, all divided by 1 plus 0.0812 times tan of 1.461. After calculating, we get Q equals 817 watts. This is the total rate of heat dissipation from the entire fin's surface. Let's review our final answers. First, the temperature at the end of the fin is 66.04 degrees Celsius. Second, the temperature at the middle of the fin is 80.14 degrees Celsius. And third, the rate of heat dissipation is 817 watts. These results show how the fin effectively transfers heat from the hot base to the surrounding cooler environment, with temperature decreasing along the length of the fin.
Problem 7 states, an experimental device that produces excess heat is passively cooled. The addition of pin fins to the casing of this device is being considered to augment the rate of cooling. Consider a copper pin fin, 0.25 centimeters in diameter, that protrudes from a wall at 95 degrees Celsius into ambient air at 25 degrees Celsius. The heat transfer is mainly by natural convection, with a coefficient equal to 10 watts per meter squared Kelvin. The thermal conductivity of copper equals 396 watts per meter Kelvin. We need to do the following. Part A, estimate the heat loss when the fin is infinitely long. Part B, estimate the heat loss when the fin is 2.5 centimeters long and the coefficient at the tip is the same as around the circumference. And part C, how long would the fin have to be for the infinitely long solution to be correct within 5%? Let's visualize this problem. Here we have a wall maintained at 95 degrees Celsius. From this wall, a cylindrical copper pin fin extends into the ambient air. The fin has a diameter of 0.25 centimeters and a length of 2.5 centimeters for part B of our problem. Heat is conducted through the fin from the base and dissipates to the surrounding air through convection, as indicated by these arrows. The ambient temperature is 25 degrees Celsius, and the convection heat transfer coefficient is 10 watts per meter squared Kelvin. Now, let's organize our given data systematically. Pin fin diameter, D equals 0.25 centimeters, which is 0.0025 meters. Pin fin length for part B, L equals 2.5 centimeters, which is 0.025 meters. Surface temperature at the base, T sub B equals 95 degrees Celsius. Ambient temperature, T infinity, equals 25 degrees Celsius. Heat transfer coefficient, H equals 10 watts per meter squared Kelvin. And the thermal conductivity of copper, K equals
396 watts per meter Kelvin. We'll keep this data visible throughout our solution for easy reference. Let's begin our solution with the initial calculations. First, we need to find the cross-sectional area of the pin fin. For a circular cross-section, the area is A sub c equals pi over 4 times d squared. Substituting our diameter, A sub c equals pi over 4 times 0.0025 squared. This gives us A sub c equals 4.91 times 10 to the power negative 6 square meters. We'll add this to our calculated values. Next, we calculate the perimeter of the fin. For a circular cross-section, the perimeter is P equals pi times d. Substituting, P equals pi times 0.0025. This equals 7.854 times 10 to the negative 3 meters. We'll add this to our calculated values as well. Now, we need to calculate the fin parameter m, which is crucial for fin analysis. The formula is m equals the square root of h times p divided by k times a sub c. Substituting our values, m equals the square root of 10 times 7.854 times 10 to the negative 3 divided by 396 times 4.91 times 10 to the negative 6. Calculating this gives us m equals 6.356 per meter. This parameter represents the rate of temperature decay along the fin length. We need two important dimensionless parameters for our fin equations. First, ml, which is 6.356 times 0.16 equals 0.16. Second, h over mk, which equals 10 divided by 0.16 times 396 equals 0.16. Notice that in this particular case, both ml and h over mk have the same value of 0.16. This is coincidental, but we'll simplify our calculations. Now let's solve case 1, heat loss from an infinitely long fin. For an infinitely long fin, the heat transfer equation is q dot equals the square root of h times p times k times a sub c multiplied by the temperature difference, T sub b minus T infinity. This formula assumes the fin is long enough that the tip temperature approaches the ambient temperature. Substituting our values, q dot equals the square root of 10 times 7.854 times 10 to the negative 3 times 396 times 4.91 times 10 to the negative 6. This entire term is multiplied by the temperature difference, 95 minus 25. Evaluating this expression, q dot equals 0.865 watts. This is our answer for part A. For an infinitely long fin, the heat loss would be 0.865 watts. Moving to case 2, heat loss from a finite fin with length equal to 2.5 centimeters. For a finite fin with convection at the tip, the equation becomes q dot equals the square root of h times p times k times a sub c times the temperature difference, multiplied by a correction factor, hyperbolic tangent of ml plus h over mk times hyperbolic cosine of ml, divided by hyperbolic cosine of ml plus h over mk times hyperbolic sine of ml. This correction factor accounts for the finite length and tip convection. Let's substitute our values. The first part is the square root of 10 times 7.854 times 10 to the negative 3 times 396 times 4.91 times 10 to the negative 6, multiplied by 95 minus 25. For the correction factor, we substitute ml equals 0.16 and h over mk equals 0.16. Hyperbolic tangent of 0.16 plus 0.16 times hyperbolic cosine of 0.16 divided by hyperbolic cosine of 0.16 plus 0.16 times hyperbolic sine of 0.16. Evaluating this complete expression, q dot equals 0.152 watts. This is our answer for part B. For a finite fin of length 2.5 centimeters and tip convection, the heat loss is 0.152 watts. Notice this is significantly less than the infinite fin case, only about 17.6% of the infinite fin heat transfer. Now for case 3. How long must the fin be for the infinitely long solution to be accurate within 5%? For the two solutions to be within 5%, the correction factor from the finite fin equation must be at least 0.95. This means hyperbolic tangent of ml plus h over mk times hyperbolic cosine of ml divided by hyperbolic cosine of ml plus h over mk times hyperbolic sine of ml must be greater than or equal to 0.95. Substituting h over mk equals 0.16, hyperbolic tangent of ml plus 0.16 times hyperbolic cosine of 0.16 divided by hyperbolic cosine of 0.16 plus 0.16 times hyperbolic sine of 0.16. Solving this equation numerically for ml and then dividing by m equals 6.356 per meter, L equals 0.2628 meters, which is 26.28 centimeters. This is our answer for part C. The fin must be at least 26.28 centimeters long for the infinitely long solution to be accurate within 5%. Let's summarize our three answers. Part A, for an infinitely long fin, the heat loss is 0.865 watts. Part B, for a finite fin with length 2.5 centimeters and tip convection, the heat loss is 0.152 watts. And part C, the fin must be at least 26.28 centimeters long for the infinitely long solution to be accurate within 5%. This problem demonstrates the importance of considering fin length in thermal design. Short fins dissipate significantly less heat than the infinite fin approximation suggests, so proper length selection is critical for effective cooling systems.
Let's solve problem 8. A hot surface at 100 degrees Celsius is to be cooled by attaching 3 centimeter long, 0.25 centimeter diameter aluminum pin fins with thermal conductivity of 237 watts per meter Kelvin to it. The center-to-center distance is 0.6 centimeters. The temperature of the surrounding air is 30 degrees Celsius, and the heat transfer coefficient on the surfaces is 35 watts per meter squared Kelvin. We assume that the heat transfer from the fin tips is negligible. We need to determine two things. Part A, the rate of heat transfer from the surfaces for a 1 meter by 1 meter section, and Part B, the overall effectiveness of the fins. Let's organize our given data. The surface temperature, Tb, is 100 degrees Celsius. The surrounding temperature, T infinity, is 30 degrees Celsius. The diameter of the pin fin is 0.25 centimeters, which equals 0.0025 meters. The length of the fin, L, is 3 centimeters, which equals 0.03 meters. The heat transfer coefficient, H, is 35 watts per meter squared Kelvin. The thermal conductivity, K, is 237 watts per meter Kelvin, and the fin spacing, S, is 0.006 meters. Now, let's begin solving this step by step. Step 1. Calculate the cross-sectional area of the fin. For a circular pin fin, the area A equals pi over 4 times d squared. Substituting, A equals pi over 4 times 0.0025 squared. This gives us 4.91 times 10 to the power of minus 6 square meters. Let's add this to our calculated values. Step 2. Calculate the perimeter of the fin. The perimeter P equals pi times d. Substituting, P equals pi times 0.0025. This gives us 7.85 times 10 to the power of minus 3 meters. We'll save this value as well. Step 3. Calculate the parameter m. M equals the square root of h times p divided by k times a. Substituting our values, m equals the square root of 35 times 7.85 times 10 to the minus 3 divided by 237 times 4.91 times 10 to the minus 6. After calculating, we get m equals 15.37 per meter. This parameter characterizes the fin's thermal performance. Step 4. Calculate the product ml. ml equals 15.37 times 0.03. This gives us ml equals 0.4611. This dimensionless parameter will be used in our efficiency calculation. Step 5. Calculate the fin efficiency for an insulated tip. Since heat transfer from the fin tip is negligible, we use the insulated tip formula. The fin efficiency, eta, equals hyperbolic tangent of ml divided by ml. Substituting, eta equals hyperbolic tangent of 0.4611 divided by 0.4611. This gives us a fin efficiency of 93.47%. This high efficiency means the fin is performing very well. Step 6. Calculate the total number of fins in 1 meter by 1 meter section. The number of fins, n, equals 1 square meter divided by the spacing squared. That's 1 divided by 0.006 squared. This gives us 27,778 fins. That's a lot of fins packed into 1 square meter. Step 7. Calculate the total finned surface area. The finned area equals the number of fins times the surface area of one fin. Each fin has a cylindrical surface area, pi dl, plus the tip area, pi d squared over 4. So, a fin equals 27,778 times, open bracket, 0.00236 plus 0.00049, close bracket. This gives us 6.68 square meters. Notice how the fin surface area is much larger than the base area of 1 square meter. Step 8. Calculate the unfinned surface area. The unfinned area equals the total base area minus the area occupied by the fin bases. A unfinned equals 1 minus n times pi d squared over 4. This gives us A unfinned equals 0.86 square meters, so about 14% of the base area is occupied by fin bases. Step 9. Calculate the heat transfer from the finned surface. The heat transfer rate from fins equals the fin efficiency times H times the finned area times the temperature difference. Q dot fin equals 0.9347 times 35 times 6.68 times 70. Here, the temperature difference is 100 minus 30, which equals 70 degrees. This gives us Q dot fin equals 15,300 watts. That's a significant amount of heat being dissipated by the fins. Step 10. Calculate the heat transfer from the unfinned surface. Q dot unfinned equals H times A unfinned times delta T. That's 35 times 0.86 times 70. This gives us Q dot unfinned equals 2,107 watts, much less than the fin surface, as expected. Step 11. Calculate the total heat transfer rate. This is answer A. The total heat transfer equals the sum of heat from the finned surface and the unfinned surface. Q dot total equals Q dot fin plus Q dot unfinned. That's 17,300 plus 2,107. This gives us Q dot total equals 17,407 watts, or 17.417 kilowatts. This is our answer A. Step 12. Calculate the heat transfer without fins for comparison. If we had no fins, the heat transfer would simply be Q dot no fin equals H times A times delta T. That's 35 times 1 times 70. This gives us only 2,450 watts. Now you can see how much the fins help. Step 13. Calculate the overall effectiveness of the fins. This is answer B. The overall effectiveness, epsilon, equals Q dot total divided by Q dot no fin. That's 17,407 divided by 2,450. This gives us epsilon equals 7.1. This is our answer B. This means the fins increase the heat transfer by 7.1 times compared to having no fins at all. That's an excellent enhancement. Let's review our final answers. Part A. The rate of heat transfer from the surfaces for a 1 meter by 1 meter section is 17,407 watts, or 17.417 kilowatts. Part B. The overall effectiveness of the fins is 7.1. This problem demonstrates the remarkable effectiveness of extended surfaces. By adding these small aluminum pin fins, we've increased the heat dissipation by more than 7 times. The high fin efficiency of 93.47% shows that the fins are well designed, and the large number of fins creates a massive increase in surface area, leading to this impressive heat transfer enhancement.